Good morning, students. Today our topic of discussion is static indeterminancy, unit 1, part 2. The learning outcomes. The student will be able to determine the degree of redundancy or degree of static indeterminancy. First we will again recall what is meant by degree of redundancy or degree of static indeterminancy. The term redundant means extra or not needed. When we provide more number of support constraints than the minimum required, the structure is externally redundant. We already discussed in the first video about external stability. So when we provide more support constraints than the minimum required, then the structure is externally redundant. When we provide more internal constraints than minimum required to make the system internally just rigid, then the structure is internally redundant. The number of redundants, that is internal or external constraints that cannot be determinable by solving equations of static equilibrium, are termed as degree of static indeterminancy. So static equilibrium is related to forces. Static is always related to forces. Equations of static equilibrium is directly denoting the force equilibrium. So we already discussed about external redundancy and internal redundancy. So we will now look at further examples for degree of static indeterminancy. So the degree of static indeterminancy is the summation of internal redundancy Ni plus external redundancy Ne minus releases. Minus, if there is any release, it has to be deducted. External indeterminancy Ne is number of reactions in the structural system minus number of static equilibrium equations. That is termed as external indeterminancy. Internal indeterminancy Ni. So the beams like continuous beams, simply supported beams, cantilever beam are internally stable. Single story rigid jointed plane frames. For these beams and single story rigid jointed plane frames, internal redundancy is 0. Internal indeterminancy is 0. For multi-story, so instead of having a single story, when you add one more story, the multi-story becomes multi-story. For multi-story rigid jointed plane frame, so one closed loop, so this also we discussed yesterday in the previous video. So one closed loop Ni will be equal to 3. So when you cut a closed loop box frame, you will have 3 unknowns, that is your internal indeterminancy Ni equal to 3. For pin jointed plane frames or trusses, internal indeterminancy is M minus 2j minus 3. Number of members deducting 2j minus 3 is the internal indeterminancy for plane frames, pin jointed plane frames or trusses. So first we will look at some of the examples for rigid jointed plane frames. Number of static equilibrium equations for a rigid jointed plane frame will be 3. So we have 3 force equilibrium equations. Summation of forces in x direction equal to 0. Summation of forces in y direction equal to 0. Summation of forces in moment about z axis will also be equal to 0. These are the 3 static equilibrium equations for rigid jointed plane frames. Again we look at the types of supports. We already know that a hinged support is offering resistance to movement in by offering a reaction in x direction, so it will not allow the structural system to move in x direction, and also it will not allow the structural system to move in y direction. So it offers two reactions, but it will allow rotation. So it will allow rotation, so the moment at the hinged support is 0. So the roller support has only one reaction. The roller support, when a force is applied like this, the roller will start rolling in this plane. In this y direction, there is a plane perpendicular to y axis, that is xz plane. So the roller will start moving in the xz plane when the force is applied in x direction. So it offers only resistance in y direction. There is a reactive support reaction in y direction. When you consider the fixed support, there are three reactions. It offers reaction, support reaction from x direction. It will not allow this joint to move in x direction. It will not allow this joint to move in y direction, and it will not allow this joint to rotate. So that is fixed support. Since the rotation is restrained, we have a reactive bending moment, reactive moment which is acting, which is restraining this rotation at this joint of the structure. So such a kind of joint is termed as a fixed support. Fixed support. All supports are special kinds of joints provided at the boundary of the structure. Supports are also joints, but they are provided at the boundary of the structures. So we now introduce one more type of support, that is guided roller. So guided roller, when you imagine in this fixed support, so perpendicular to this x axis, when you provide rollers, so imagine when you apply a vertical downward shear force here, then roller will start rolling. So when you release Fy, the support is termed as guided support. So Fy becomes nullified. So when you allow movement in y direction, but fixity is maintained in such a way that movement is restrained only in x direction, but movement and also rotation is restrained, but the movement in y direction is allowed. Such a force release is termed as guided roller. Such a support is termed as guided roller. Guided roller has two reactions, one horizontal horizontal support reaction and a moment. So these are the common types of supports. We further look into the common types of joints within the members. So within the member, so when there is a structural element, when you cut a plane frame element, what are the internal force resultant we find in a plane frame element? In a plane frame element we find axial force, shear force and a bending moment. Axial force, shear force and a bending moment. You cut a plane frame element, we have three internal forces: an axial force, a shear force and a bending moment. So when in this plane frame structural element, when you try to release any one of the force, in order to allow movement in that direction, it becomes a internal joint. So already we discussed two types of internal joints provided at the connecting points of structural members. The internal joints are used for connecting they assure that the connecting members stay together and they move together in such a way that we allow the movement. The movement is allowed as per our wish. So when the joint between structural element is rigid, so it is a rigid, all the movements are constrained. So all the movements are constrained in a rigid joint. In the pinned joint, so we have rotation is released. When moment is released in a rigid joint, it is becoming a pinned joint. So we already introduced these rigid joint internal joints such as rigid joint and pinned joint. So within structural element we can also release some of the forces. So there are three forces in which we try to release something. So vertical shear release due to guided roller. So when you introduce a guided roller within the beam element or any structural element, we release Sy. So vertical shear is released. Why it is said it is released? So in this after introducing this guided roller, when you apply vertical force here, so this will go down, but this movement will not be transferred here. So there is no resistance in y direction, there is no internal force resultant in y direction. Shear in y direction is released, but there is a axial force and a bending moment. So in a plane frame element, we should have an axial force, shear force and a bending moment when you cut anywhere, but you can release any one of these three or any two of these three as per our wish by introducing internal joints. So this type of guided roller is also designated by something like this, by two vertical lines with rollers. Otherwise simply it may be designated by two vertical lines. So when a guided roller is introduced in between a plane frame element, one shear force Sy is released. Sy becomes 0 when only axial force and bending moment is transferred from one part of the structural element to the other part of the structural element. We have only axial force transfer and bending moment transfer. So number of release is 1 in case of guided, in case of vertical shear release due to guided roller. Another type of internal joint is internal hinges. Internal hinges may be introduced within the structural elements or at the boundary of the structural elements here, or likewise we can introduce internal hinge. Number of releases, force releases for internal hinge is 1. What is released due to internal hinge? Already we discussed the internal hinge in the previous video. Moment is released due to the introduction of internal hinge. So when you apply a force here, we have an internal hinge. So the due to the force we have downward displacement in the right part of the beam, and also the beam bends in the left in this particular internal hinge. So the bending moment is released. So we have bending. If you don't have internal hinge, so there will be bending moment all the points. We release the bending moment. So it is a beam element when it is subjected to common inclined type of horizontal loads and vertical loads or inclined type of loads. Anywhere within the member we have three forces: axial force, shear force and a bending moment. When one bending moment is released at this point due to internal hinge, so the deflected profile will be something like this. When there is load here, it will be in have flexural deformation will be curved in this part. When there is no load at this point, this line will be straight. Here we have a cantilever, propped cantilever beam. So this beam is termed as a continuous beam in which at one point moment is released by introducing a internal hinge. So this is a propped cantilever beam, a cantilever with a propped support. So the internal hinge which is introduced here will have, so when you look at the force transfer, when you have an inclined force here, so this will be resisted by this internal hinge by developing a horizontal reaction and a vertical reaction. Moment will be equal to 0, moment at this point. So it is like a broken, broken but connected. Likewise it behaves, internal hinge. So it is vertical force is transferred, axial force is there. Inclined force can be resolved into two components, one vertical component and one horizontal component. One vertical component will be shared by these two vertical reactions, and horizontal component will be resisted by this horizontal force at the hinge. So this horizontal force and vertical force will be transferred to this beam, other part of the beam. Only force is transferred, no moment is transferred at this beam. So moment is 0 at this roller support. Moment increases, there is a moment up to this point. At this point moment becomes 0. And you have further moment increases from this point to up to the fixed support due to this force transfer from this part to this part, axial force and vertical shear. So we have a support reaction. So this is support reaction, roller support, and this is support reaction, vertical reaction in the fixed support, horizontal reaction, and a moment in the fixed support. So number of releases due to a internal hinge is 1. Internal hinge is equal to 1. Internal hinge in a rigid jointed plane frame. So in a rigid jointed, so this is a rigid jointed plane frame. So here it is base, and along the horizontal direction it is termed as base, along the vertical direction it is termed as stories. So it is a two-story plane frame. So it is a multi-story, since it has 2 stories, it is a multi-story plane frame, rigid jointed. So all the joints are rigid joints. So here rigid jointed, we only mentioned the internal joints. The term rigid jointed plane frame, we mentioned that the joints between the members are rigid. Joints between the members here are rigid. So when you introduce a internal hinge here, internal hinge in a rigid jointed plane frame, the additional moment releases due to internal hinge will be m minus 1, where m is the number of members connected to that hinge. So additional moment releases are, so you consider number of members here 1, 2, 3, 4. 4 minus 1, 3 is the additional moment releases we get by when 4 members are connected. So additional moment releases we get is 3. So here we have 2 members are connected. So 2 minus 1, you have 1 release. One number of releases is 1. So here number of releases is 4 members are connected. 4 minus 1, number of releases is 3. So we can have one more type of internal joint between a member. Between a member, when you introduce a roller something like this, so now you apply a horizontal force here. So you try to apply a horizontal force here. So what happens? So due to this roller, the member moves in this direction. So no axial force. When you apply the load something like this, axial force. So axial force is not transferred, and you apply a moment. So it will go down due to the presence of this roller. Roller will not have any resistance against rotation, so it will try to rotate. So when you try to release two axial forces and bending moment, you can introduce the internal roller. Now only the shear force from one part of the element will be transferred from the other part, from the one part to the other part. So now here, when you have a vertical load, shear force will be transferred from here to here. Since we have a connection, how could you remember these things? So when you look at this, you find the difference between these two. So this pinned joint, you have beam is connected here and here, so the shear is transferred. The beam goes down, hence the axial force will all connected here, so axial force will also be transferred. Only bending moment becomes 0. So beam bends here, bending moment will be there will be a downward deflection when you connect the hinge something like this. But when you connect the roller something like this, so the axial force will not transfer, but we have connection between roller and the structure here, so it will transfer vertical force. So it will not transfer axial force, it will not transfer bending moment, it will transfer only shear force. Number of releases are 2. What is a release? Release is what is made 0 is termed as a release. So here, what are the releases? If due to a internal roller within a structural element, bending moments and axial forces are released. Number of releases are 2 in case of a internal roller. Internal link, we can also have an internal link. So now you imagine here also, when you connect the two members by means of this link here. So here also, when you apply a horizontal force, so the link goes something like this, it becomes inclined. The link accepts only axial force, so it accepts only axial force, hence shear, only vertical shear is transferred. And here also bending moment and axial force are 0. Here also number of releases are 2, bending moment and axial, it accepts only axial force, link accepts axial force, hence only shear. So for the beam, the force is transverse, which is shear, which is axial force for the link. So the link accepts only axial force, hence only shear is transferred from this part of the element to this part of the element. So when you make a connection something like this, you can make bending moment as 0 and axial force as 0. No axial force. When you have axial force, when you try to push this link, the link will go in this way, it will not accept any force transfers to its longitudinal direction. What is the longitudinal direction for a link? Link is along this direction, so when you push it will go in this way, the link becomes inclined due to axial force. But so the axial force will not be transferred from, when the movement is allowed, the force will not be transferred. So the axial force and bending moment also, when you have a bending moment, the link becomes again straight, becomes inclined, only the shear force is transferred. So bending moment and axial, number of releases is 2 due to internal link. So you can have axial force release also. So imagine within a structural element you have a you make a arrangement something like this. So here you introduce rollers in this direction. So when you make a arrangement something like this, then when you introduce rollers here, when you apply a axial force, so this axial force will not be transferred. The rollers will start rolling in due to the axial force. When you apply axial force, roller will move in this direction. So when movement is allowed, that force is released, axial force is released. So number of releases is 1. So this axial force release can be introduced by arrangement something like this, but the other two internal force resultants such as shear force and bending moment are transferred from one part of the structural element to the other part of the structural element. Only axial force is released. So what we discussed in this cases is, when you want to release only bending moment, you should have a internal hinge. So when you want to have only shear released, then only shear force should be present, and other two releases, bending moments and axial force, when you want to become 0, bending moments and axial forces, then you can have either internal roller, otherwise you can have internal link. So when you want to make only axial force to be released, then you can have such arrangement to have axial forces released, only other things are transferred. When you want to have only shear forces to vertical shear forces to be released, other two has to be transferred, then you can have a guided roller within a structural element. So these are some of the internal joints that is possible within the elements. So now we try to calculate the degree of static indeterminancy for a continuous beam. So it is a continuous beam, it is subjected to a inclined load. Now what are the number of equations of static equilibrium? 3. You have 3 equations of static equilibrium for a plane frame element which is subjected to any beam element or plane frame element. It is subjected to inclined loads. Then beam with inclined loads or plane frame elements, we have 3 equilibrium equations. Summation of forces in x direction equal to 0, summation of forces in y direction equal to 0, and moment about the point, any point, will be equal to 0. So a fixed support has 3 support reactions, 1, 2, 3, and this hinged support will have only it is within the member, so only one vertical reaction. This roller support so has a vertical reaction, and this hinged fixed support has 3 reactions, support reaction. So it is a within the member, fixed support is at the boundary of the structure. So you count all this 1, 2, 3, 4, 5, 6, 7, 8. So internal indeterminancy is 0. These are stable beams and plane frames, single story plane frames are stable structures, internally stable configurations. The geometric configuration is stable, so Ni is 0. Internal indeterminancy is related to geometric configuration, arrangement of the members to carry the load when we arrange the members. So when we provide more number of constraints, restraints, more number of members, then internal indeterminancy increases. So here if this internal indeterminancy is 0, External indeterminacy is support reactions. Number of support reactions are 8 minus 3 equilibrium equations, 3 releases. There are no force releases. Force releases are 0. So 8 minus 3, you have 5 is the degree of static indeterminacy for this continuous beam. So when you look at this example, a plane frame A, B, C, D, E, F, G, H shown in figure has a clamp support at A. Clamped support is a fixed support. Hinge support at H. Roller support at G. Also it has axial force release at C, and it has a internal hinge at E. What is the degree of static indeterminacy? So you count the reactions. Here the reactions are 3 fixed support, a hinged support reactions are 2, roller support vertical reaction, only one vertical reaction is 1. So 3 plus 2 plus 1, 6 is the number of reactions, minus number of equilibrium equations are for a continuous beams and continuous beams with inclined loads and plane frames, rigid jointed plane frames. We have 3 equations of equilibrium. So 6 minus 3 is your number of reactions minus number of equations. Single story is internally stable. Single story structures are internally stable. So Ni is 0. Releases, here you have 2 releases. Here one axial force is released. Here connected members are 2. So 2 minus 1, 1. One moment is released. So number of releases are 2. One axial force release and a 1 moment release, internal hinge. So releases are 2. 6 minus 3, 3 minus 2, 1 is the degree of static indeterminacy. So degree of static indeterminacy is very less. Here by it is can be solved easily. When the degree of static indeterminacy is less, it can be solved by the designer very easily. So we discussed 2 examples for plane frames, one continuous beam and one rigid jointed plane frame. So this is a continuous beam and this is a rigid jointed plane frame. These joints are rigid. 2 examples for rigid jointed plane frames. Now we discuss the rigid jointed space frame. Number of static equilibrium equations are 6 for a rigid jointed space frame. So space frame is 3-dimensional. So you have forces and moments in all the 3 directions. So number of static equilibrium, force equilibrium equations available are also 6. Summation of forces in x direction equal to 0. Summation of forces in y direction equal to 0. Summation of forces in z direction is also equal to 0. Summation of moments about x axis is 0. So summation of moments about y direction is also equal to 0. Moment about z direction is also equal to 0. So these are the 6 static equilibrium equations for a rigid jointed space frame. You have 6 equations. So in 3 dimension, when you imagine a fixed support in 3 dimension, you have 6 reactions. So when you fix it completely, the support will not allow movement in y direction, x direction and also in z direction. We have reactive forces in all the 3 directions: support reaction x, support reaction y, support reaction z. So you have all support reactions from all the 3 directions when you fix it completely. So a fixed support in 3 dimensions. So you imagine a beam, cantilever beam inserted within a wall. It is a fixed support. Cantilever beams are inserted within a wall, and you do a three-dimensional analysis. Then that fixed support will have support reaction. Three-dimensional, it have support reactions in all the three direction and moments. It will offer resisting moment about z-axis. So moment about z-axis is this. So it will induce bending like this. Moment about z-axis. Moment about x-axis is twisting. Moment about x-axis is twisting. Moment about y-axis is perpendicular to the screen. The bending curve will be perpendicular to the screen. You look at the movement of the cursor. So you have bending curve is along the plane of the screen due to you imagine the deflection curve. MZ will have a deflection curve along the plane of the screen. My will have a deflection curve perpendicular to the plane of the screen, and mx will induce twisting, moment about x. So this support offers resistance to movement in all these three directions. So fixed support offers reaction, 6 reactions, 3 bending moments and 3 force reactions. A fixed support, a roller support in 3 dimension. When you imagine a roller support in 2 dimension, it offers only vertical reaction. In 3 dimension also. So when you when you imagine the plane which is perpendicular to this y-axis is xz plane. So when you provide a roller support in the xz plane and you apply force in z direction, force in x direction is this, z is this. So this xy plane, y-axis, x-axis, xy plane, perpendicular is z. So when you apply a force in x direction and x direction, then the roller will roll. When you apply a force in z direction, z is this direction, the roller will roll. When you apply a force in x direction and when you apply a force in z direction, the roller will roll in the xz plane. Xz plane is the plane perpendicular to the y-axis. So there is no resistance in both the directions, so only one support reaction, as in the case of 2 dimension, in case of a roller in 3 dimension. When you do a 3-dimensional analysis for a roller, then you have there also you have only one support reaction. When you imagine a hinged support in 3 dimension, when you provide a hinged support, so it offers resistance in, so it will not allow the movement in x direction. When you pinned it here, it will not allow the movement in z direction, x direction and y direction. So all the directions, when you try to apply a force in z, it will not move. Apply a force in y, it will not move. Apply a force in x, it will not move. But apply a moment, it will rotate. Apply a moment, this is z moment, it will rotate something like this. And when you apply a y moment, my moment, it will bend something like this, perpendicular to the screen. So pinned support in 3 dimension, hinged support or pinned support in 3 dimensions has 3 support reactions, 3 force resultants, 3 force reactions. Reactions are offered from the support. When you imagine a guided roller in 3 dimension, so when you imagine a guided roller in 3 dimension, when you provide the guided roller, so there is a plane perpendicular to x-axis. The guided roller only restrains movement in x-axis. There is a plane, YZ plane. The roller rolls on the YZ plane. So when you apply a force in y direction, the roller will roll down. When you apply a force in z direction, the roller will force towards this left. So the movement is happening when due to the roller, the movement is happening in the YZ plane. So there is no Fy, there is no Fz. So you have only movement is restrained in x direction. So you have 4 reactions. but due to fixity you have rotation is restrained in all the directions. You fixity is introduced here, so it is three dimensionally the fixity is present. Only the movement is allowed in the x or in the y or z direction. Only x direction you have restrained. So you have 4 reactions in a guided roller in 3 dimension, force in x direction and other 3 are moments. All the 3 moments are present. When you try to apply force in z, it will roll in the yz plane. When you apply force in y, it will roll in the yz plane. No restraint for displacement in y or z direction. Only displacement rotation is restrained in y direction, x direction and z direction. So that is the guided roller behavior in 3 dimension. You have 4 reactions. So now you look at the internal hinge. How does a internal hinge in a rigid jointed space frame behaves? So the additional moment releases due to in 2 dimension you have only m minus 1 releases. Due to a internal hinge you have only m minus 1 releases. In 3 dimension you have 3 into m minus 1 releases. The additional moment releases due to internal hinge in a space frame will be 3 into m minus 1, where m is the number of members connected to that hinge. M is the number of members. So when you imagine there is a hinge here, you have 4 members connected, 1 2 3 4 4 members connected. When you 4 minus 1 3 3 into 3 9. Additional moment releases are 9. We have moment releases in 9 directions when you introduce a hinge between a connection of 4 members. So additional moment releases available, equations available for solving will be 9. So releases are detected. So now as an example we will calculate the degree of static indeterminancy for a space frame. So this is a space frame, only single story space frame. Here you have a fixed support. At this end you have a pinned support. At this end you have a pinned support. At this end you have fixed support. A fixed support in 3 dimension offers reactions in 6 direction. So when you fix it firmly to the ground 3 dimensionally, the movement is arrested in x direction, the movement is arrested in y direction, the movement is arrested in z direction. The rotation in z direction is arrested, rotation in y direction is arrested, rotation about x axis is also arrested. So you have 6 support reactions for a fixed support in a space frame. So here also 6, and pinned support will have only 3 support reaction: force in x direction, force in y direction and force in z direction. 3 support reactions. So when you sum all these 6 plus 3 plus 6 plus 3, total number of support reactions from the ground will be 18. Number of reactions are 18. Number of equations are, so the degree of static indeterminancy is internal indeterminancy, external indeterminancy minus releases. So the support reaction internal indeterminancy is 0. For a single story it is stable. Single story is always stable. So internal indeterminancy is 0. External indeterminancy is 18 minus number of equilibrium, force equilibrium equations are 6 here. Force equilibrium equations are 6. So number of reactions minus number of force equilibrium, 18 minus 6 minus releases. Minus releases. How do you find number of releases? There is a internal hinge here. If there is no internal hinge, release becomes 0. Now we have an internal hinge in 3 dimension. internal hinge in 3 dimension, a 3-dimensional space frame, a internal hinge is introduced between two members. So you have two members are connected, 2 minus 1 1 1 into 3 moment releases are there. So you have 3 moment releases are there. So moment by introducing this internal hinge, all the 3 moments are released here. All the 3 moments are released here. So you have 3 releases, 3 into m minus 1, where m is the number of members connected. So do you understand this? Due to this moment release, you have moment is released in x direction, y direction and z direction. So 3 releases are there. But in 2 dimension only one moment is released, mz. Only mz is released due to internal hinge in 2 dimension. Internal hinge in 3 dimension releases all the 3 moments. So minus 3. So why do you detect it? 3 releases will offer us 3 conditions to find the forces. So when you want to find the solve this joint, you can take moment about this joint and find the forces at this joint. So this releases are giving us additional conditions to solve the problem. Releases are given. When you take moment about this point, you can find the axial force at this point. When you have an axial force, when you have a support reaction here, it will be equal to the axial force here. You have, when you have a reaction in this x direction, you have a reaction in this direction, which can be found by taking moment about this point. So releases are offering us additional conditions. So these are detected. So this makes the problem solvable. So these are detected. So you have degree of static indeterminancy 18 minus 6 is 12. 12 minus 3, 9 is the degree of static indeterminancy or redundancy. Extra when you find all this 9, the problem will be easily, you can draw the bending moment shear force diagram. That is internal for all the force resultants at all the points can be found easily when you know these 9. Only when you know this 9 values in space. So what are these 9? That is our choice. So which 9 we have to find out, that is our choice. So the degree of static indeterminancy here is 9. So we discussed about the degree of static indeterminancy for plane frames, and we have also looked into a example of space frames. Thank you.